A, B and C have given us a chance to think about populations. Now what we can do is think about what happens if, instead of just looking at an individual fund from this population and working out the probabilities, we can think about what happens when we take a sample. And to do that, we need to consider the sampling distribution. So the next bit of information tells us if you selected a random sample of 10 funds from this population, what is the probability that the sample would have a mean return? In part D, we want to find the probability that the sample would have a mean return less than 0. So this sample of 10 funds, if you get the average return, what's the probability that on average it made a loss? As soon as we start talking about taking a sample from the population, to be able to answer probability questions, we're going to be looking at the sampling distribution. And that means our random variable is x bar. X bar is the sampling distribution. We need to think about what its characteristics are so that we can then solve our calculation questions. Now, the population was normal, so the sampling distribution is also normal. So that's the first step. If we know the values of the population, we know the values of the sampling distribution. So remember, the rules or the theory tells us that the mean of the sampling distribution will be the same as the population mean, and so x bar will have a mean of 5.13. Standard deviation of the sampling distribution is also linked to the population, but to get the standard deviation of the sampling distribution, we've got to look at sigma divided by the square root of n. So in this case, the standard deviation of the sampling distribution will be 6 divided by the square root of 10. But once you've got those two values, once you know the mean of the sampling distribution and the standard deviation of the sampling distribution, and while we know it's normal, so this is really just a normal probability question. We want to find the probability that x bar is less than 0. To do that, we still have to convert it into a z-score because we don't have tables for a normal distribution with mean of 5.13 and standard deviation of 6 divided by the square root of 10. So all we do is we get our x bar value 0, we subtract the mean, and then we divide by the standard deviation. Remembering, of course, that standard deviation of the sampling distribution is 6 divided by the square root of 10. But the z-score formula is still that same format. We've just implemented it using the mean and the standard deviation of our sampling distribution x bar. Put that into your calculator and the equivalent z value is negative 2.70 if we round to 2 decimal places. So can we find the probability that z is less than negative 2.70? Yes, this is a direct lookup from the tables and it comes out at 0.0034. Now E and F are pretty much the same technique. We want to find probabilities relating to x bar, the sample mean, and to do that we have to convert to z. So let's look at E. E is the probability that x bar is between 0 and 6. Now each of those values have to be converted to a z-score. 0 has already been converted to a z-score in part D. We know it's negative 2.70, but we still have to change 6 into an equivalent z-score. So it's 6 minus the mean divided by standard deviation. Put that into your calculator and you end up with 0.46. So if I want to find the probability that my sample mean is between 0 and 6, that is equivalent to finding the probability that z is between negative 2.7 and 0.46. Can we find the z probability? Well, yes. This is, again, just back to a Level 6 problem. We can use the tables. It's an in-between probability, so it takes a little bit more work. You've got to firstly look up the probability that z is less than 0.46. That gives you the larger area. You then subtract the bit you don't want, which is the probability that z is less than negative 2.7. Put that all into your calculator and your final answer, the in-between area, is 0.6733. Part F is the probability that x bar is greater than 10. So we want to find the probability that if we take this sample of 10 funds, that the sample has a mean of 10 or more. Well, greater than 10. Remember that equals doesn't matter when it's a continuous distribution. So can we find the probability that x bar is greater than 10? Well, yes. Just convert it to a z equivalent probability question and then use the tables. So to change 10 into an equivalent z-score, we need to subtract the mean of the distribution, 5.13, and then divide by the standard deviation of the distribution, which is 6 over the square root of 10. Put that into your calculator and the equivalent z-score is 2.57. Now remember, the tables do less than probabilities. So if you look up the probability that z is less than 2.57, that will give you the complement to the area you want. So you look up the less than probability, but then just subtract it from 1, and it leaves us with 0.0051, which is the answer we're looking for. So D, E, and F are all opportunities to apply the sampling distribution theory, which tells us if we know the population, we know about the sampling distribution. There's the link between the population parameters for mean and standard deviation and the sampling distribution parameters for mean and standard deviation. We can take advantage of those to solve x bar probability questions, but of course to actually come up with the final answer, everything still needs to be converted to z so that we can use the tables. Now you've probably noticed that we did pretty much the same questions for x and for x bar. Now that brings up the question of, well, how did the answers differ? And let's just compare for part A and D. So in part A, we were looking at the probability that x is less than 0, whereas in part D, we were looking at the probability that x bar is less than 0. Now, part D had a much smaller answer than part A. Now, why is that? Well, it's all based on thinking about the fact that when you have the population standard deviation, which in this case is 6, the sampling distribution standard deviation is always going to be less. It's going to be a smaller standard deviation. And that's because to get the sampling distribution standard deviation, you start off with the population result, but then you divide by the square root of n. So the population standard deviation is 6. The sampling distribution standard deviation is 1.897. So the sampling distribution standard deviation, which we also call standard error, is less than the standard deviation of the population. This will always be true. So visually, our sampling distribution x bar has much smaller dispersion than the population x. So in terms of practical problems, you can see that, well, if we were looking at the individual funds, so we were looking at the population, when we found the probability of being less than 0, it was almost 20% of the distribution because we had the larger dispersion. When we looked at the sampling distribution, because the dispersion is much smaller, when we looked at that same sort of cutoff point of 0 and said, well, how much error is below it, there was a much smaller part of the distribution because the majority of values were close to the mean. So that's pretty much what part G is asking you. And it comes down to the whole idea that because the standard deviation in the sampling distribution is smaller, more of the values will be closer to mean. So when you find something like we've done here, the probability of being less than 0, we get a smaller area in the sampling distribution than we do in the population distribution, simply because of that reduced standard deviation in the sampling distribution. So in many ways, you can tell a lot about these distributions before you even put the numbers in.